Good morning, everyone. I am M. Venkatesh, working as an assistant professor in Triply Department in PVR Viswadaya Institute of Technology and Science, Kavali. In this video, I explain about the characteristics of DC generators. So here we learn about the characteristics of DC generators. First, we can see how to develop the EMF in the self-excited generators. So in the self-excited generator means the armature winding can excite the field winding. So that is a self-excitation process. So in these self-excited generators classified into three types, that is shunt generators, series generators and compound generators. So in these all generators, they can build the EMF. They require some requirements, some conditions. So what are the conditions required to develop the EMF in the self-excited generators? So here we can see, so if there is no, if we can take a DC shunt generator or series generator or any self-excited generator. So here, if there is no field current, that means what? There is no armature voltage. There is no speed of the generator. But in the self-excited generator, if there is no field current also, it having some armature voltage. So that voltage is called no load voltage. That voltage develops due to the residual magnetism property. So this residual magnetism property can develop the field flux. So due to developing of the field flux, they develop the speed. So that's why they develop the EMF in the generator. So in this self-excited generators, so the resistance of the field circuit always less than the critical field resistance, and speed of the generator is always more than the critical speed. At that time only the EMF developed in the self-excited generator. Okay, so then here, so what is the critical field resistance? What is the critical field resistance? It is a field circuit resistance. That resistance is useful for the excites the generator. That resistor useful for the excites the generator. That means the resistance at which generator just excites and starts the voltage. That resistor is called critical field resistance. And what is the critical speed? What is the critical speed? It is the speed at which the generator just excites, just starts the running. So that is the critical speed. So this critical speed always in the self-excited generators, the speed of the generators is always more than the critical speed, and the speed of the critical field resistance is always less than the normal resistance value. Okay, so these are the main. Okay, so here the critical field resistance and critical speed. So critical field resistance is nothing but just excites the generator and starts the voltage. That resistance is called critical field resistance. The speed just starts the mission, just starts the excitation, and the speed. So that speed is called critical speed. Okay, so then characteristics of DC generators. What type of characteristics are DC generators? So basically the two types of characteristics. So that is magnetization characteristics and load characteristics. So the load characteristics are classified into two: internal characteristics and external characteristics. Okay, so magnetization characteristics. What is the magnetization characteristics? So what is the magnetization? So magnetization is nothing but the no load voltage into field current. That is the magnetization. So in the magnetization characteristics plotted between the no load induced EMF and field current. No load induced EMF and field current. That is the magnetization characteristics. So in this, we are plot the graphs between no load voltage. That means the output side is open terminals. So that's why the load circuit is open. So when it is open means what? So it is a open circuit characteristics. It is also open circuit characteristics, and also it is called as no load saturation characteristics. Why you are calling this means, so these characteristics plotted between no load induced EMF and field current. Okay, so these magnetization characteristics or open circuit characteristics same for all type of generators. Same for all type of generators in practical. Okay, so then coming to see load characteristics or internal characteristics. So the internal characteristics is plotted between the induced EMF in the generator and the armature. So we plot the characteristic graph between the induced EMF, that is a generator induced EMF as EC, and armature current. We get the internal characteristics. So these characteristics also called as total characteristics. Coming to last, that is a load characteristics. So that is the external characteristics. So the external characteristics in the name indicates external characteristics. External means the output. So the external of the circuit. What is the external of the circuit? The voltage across the load and load current. So that's why we plot the characteristics between, plot the graph between terminal voltage versus load current. It gives the external characteristics. Okay, so then let us see the characteristics of separately excited DC generator. Characteristics of separately excited DC generator. Let us see the circuit diagram here. So the separately excited DC generator, it consists of separate field winding and separate armature. So in the separate field winding, can get the supply as separately. So at that time, we are applying the supply to the field. Field can excite and then they induce the fluxes, and that flux cut the armature conductors. Due to the cutting of armature, they develop the induced EMF. And see in the observe in the circuit diagram at the armature output terminals. So there is no load connection. So if it is connect the load, it gives the load characteristics. If there is no load, it is not giving the any other characteristics. Okay, so in the separately excited DC generators, so at the output terminals, you can see the voltmeter is connected across the armature only. There is no load. So here it gives the open circuit characteristics. So from this circuit diagram, you can simply take the voltmeter reading by changing the speed of the armature, and by get note down the field current values and armature voltage values. So here you can take the graph between that no load voltage and field current. So initially it having some voltage that is placed in the OA point, that is placed. So that OA having some voltage drop. So that voltage drop we are getting due to the residual magnetism under the no load condition. So that residual magnetism can produce some voltage drop, that is OA, and after that they develop the induced EMF, by changing the field currents, by vary the field currents. So by increasing the field current, similarly the induced voltage is going to be increased. Load voltage is going to be increased. So observe in this graph, you can change the speed levels N3, N2, N1, different type of speeds. So when increases in the speed, the induced of armature voltage is also increases. So in this graph, the N3 is greater than N2 is also greater than N1 speed. So this N is nothing but speed of the generator, that speed in RPM. So the N3 greater than N2 greater than N1. Okay, this is the open circuit characteristics. Let us see internal characteristics. Let us see the internal characteristics of the separately excited DC generators. So under no load voltage, so under the initial condition, the no load voltage is constant. It is plotted as AB. It is plotted as AB. So in this AB, that is the no load voltage versus load current. So no load voltage versus load current. So after when we are providing, it is a separately excited, and after getting the excitation, it produces the constant voltage. It produces the constant voltage that plotted the graph, that is the AB line. So then when we are applying the load here, when we are connected to the load, so, and also when the develop of the induced EMF in the armature, when the develop of induced EMF in the armature, so they have some armature reaction. That means the main pole flux on the field pole flux, the main pole flux on the field pole flux. So that means the main MMF versus field MMF. So they have some variations. Due to that, in the armature having some internal resistance, that is a RA, the armature resistance. Due to the armature resistance, they have get some armature drop, some armature drop. So that armature reaction drop presents. So that's why in the internally they develop some voltage drop, that is armature drop. So due to the drop, the actually having the maximum amount of voltage, but after that, after getting the induced EMF, after developing the generated EMF in the armature, they lost the voltage. That loss is taken as armature reaction drop. So due to that, so we plot the graph between the induced EMF, generated EMF versus the field current, generated EMF versus field current. That is nothing but armature current. Due to that, the graph shows AC. The graph shows AC. So that AC is called so internal characteristics. That AC is called internal characteristics. And then after that, after some time, we are connecting the load. After getting the excitation, we are connecting the load. At load characteristics, we plot the load characteristics at the load. So at load, we are connecting the voltmeter. So that is giving to the reading of terminal voltage, and then we have take the reading of load current. In the load current, so when we are connecting the load, they have some internal resistance. They are also having some voltage drop. So when we are connecting the load, the maximum amount of current passing to the circuit. So due to that, the armature having the copper winding, so that armature reaction presents. So due to that development of voltage, so there's some ohmic losses. There some induces the maximum amount of current. They develop the maximum amount of voltage. So due to that, we are getting some loss. That is a ohmic loss. That loss is nothing but so copper loss. So that copper loss, we are getting later some voltage drop due to the presence of some voltage drop, ohmic voltage drop presence in the armature. That is near to the load. So in the load connection point of view, we plot the characteristics between the terminal voltage at the load versus load current. We are getting the AD characteristics. This AD is nothing but external characteristics of the separately excited generator. This process, we are getting the demagnetization effect on the armature reaction. So due to this, we are getting the some armature reaction drop and the ohmic reaction drop in the graphs. Okay, so next we can see characteristics of DC shunt generator. Let us see characteristics of DC shunt. Okay, so now we can see characteristics of DC shunt generator. So it is a self-excited DC generator. So in the self-excited DC generator, they develop the EMF due to the armature winding. So initially there is no field current, but they have some internal voltage that due to the presence of residual magnetism in the machine. So that's why. So here some initial voltage. So that voltage is taken. That voltage getting by the residual magnetism property. So that voltage plotted in the OCC characteristics as previous we see. So that is the same here. So let us see in the internal and external characteristics of DC shunt generator. So in the internal and external characteristics of DC shunt generator, so initially to run the mission by using to run the generator by using a prime mover. So that prime mover can use the mechanical energy to the armature of generator. So this armature excites and get the rated speed. Get the rated speed. That means fully excited. So at this case, there is some demagnetization effect. So initially they have some constant voltage. So there is a no load voltage to load current. We get the constant voltage at the constant speed. So constant speed, that is a AB. So here AB line indicates the, so here AB line indicates the a constant voltage under the constant speed of the generator. So after that, so in this armature, they develop the EMF. They develop the EMF. So it builds the EMF. So during the building of EMF, they have some armature reaction, and that is the demagnetization effect. So due to the demagnetization effect, they have some armature reaction drop. So that having the voltage levels. So if we are increasing the induced EMF, so if we are increasing the armature current, to increase the armature current, the induced EMF, generated EMF is may vary to decreases due to the change of arm, slightly decreases due to the demagnetization effect. So then draw the external characteristics, that is we take the load voltage versus load current. So when we are connecting the load, by varying the load, that means to increase the load current, the generator, the load voltage may also varies due to the variation. That means due to the getting of some voltage drops, some voltage drop presents across the load point. So initially we having some armature reaction drop, and after that we are getting some more voltage drop due to the load. So that's why this voltage of this terminal voltage also decreases than the internal voltage, characteristics. So that's why the external characteristics, so plot versus the terminal voltage versus load current. If increasing the load current, the terminal voltage may decreases from constant voltage to minimum value. In this graph, the AB indicates the constant voltage. It is between no load voltage versus no load current, and then so the pink, that is the AC, indicates the internal characteristics of the DC shunt generator. So in this AC, slightly reduced than the constant voltage saturation point, that is due to the armature reaction. And AD line indicates the external characteristics of the DC shunt generator. So here also you can observe some voltage drop. This is the characteristics of DC shunt generator. Okay. So in the DC shunt generator, so it is already explained. So internal and external load characteristics. So by developing the induced EMF. So by developing the voltage before applying any external load. Okay. So that is. So let us see characteristics of DC series generators. So in the series generators, we simply observe the current. The armature current is equals to the series field current, that is also equals to the load current. That means if we can plot the either OCC characteristics or internal characteristics or external characteristics, only a constant x-axis, that is a load current, is the constant x-axis. So initially you can plot the OCC characteristics. So OCC characteristics means what? Open circuit characteristics. This open circuit characteristics plots between no load induced EMF versus no load current. That means no load induced EMF versus field current. So here the field is series field. So that means the series field current. That series field is also same as load current. That's why I take the on x-axis load current. So initially any generator, they have some constant voltage due to the residual magnetism. So it having some initial voltage, that is a OA. OA indicates the some initial voltage value. that voltage. So we start the curve from A onwards. So that's why the OCC characteristics starts from A onwards. So and still by increasing the load current, by changing the field currents, so the OCC also increases after the up to getting the saturation point, up to getting the saturation point. Okay, that is the open circuit characteristics. In the internal characteristics, so if we can plot the internal characteristics also, if between that induced EMF versus load current, induced EMF versus armature current. So in this series generator, armature current is nothing but load current. So that's why this induced EMF may starts from 0 to saturation point. But here some demagnetization effects and cross magnetization effects, we are getting some armature reaction drop. So the internal characteristics curve some lesser voltage than the OCC characteristics. So here OC indicates the internal characteristics of the DC series generator. So similarly, external characteristics. So when connect the load, we can increase the load value. By increasing of load value, so by increases the terminal voltage. So when the terminal voltage increases up to saturation point, so that means up to constant voltage value. After that, after the saturation point, we are increasing the load current. That terminal voltage may going to be 0. Terminal voltage is going to be 0. Okay, so this is the external characteristics. So in this graph, so you can observe OA is the voltage, no load voltage due to the residual magnetism. AB is the OCC characteristics. OC is the internal characteristics. OD is the external characteristics. Okay, so in this characteristics, so if terminal voltage increases with the load current increases. Terminal voltage increases with load current increases. Okay, in this series generators, so the load current increases, the field current also increases. If load current increases, field current also increases. Why? Because it's IA equal to armature current equals to series field current equals to load current. So that's why if load increases, series field current increases. If series field current increases, armature current also increases. So in the external characteristics, when the voltage reaches to a certain limit, so again it is going to be decreases when increasing the load current. So this is simply excessive of demagnetization effect. This is the characteristics of DC series generators. This is the characteristics of DC series. Now we can see the next characteristic is characteristics of DC compound generator. So the compound generator consisting of series field and shunt field. Series field and shunt field. Okay. So here the characteristics, the OCC characteristics is same for the DC shunt generator, series generator and compound generator. But coming to in the internal and external characteristics may vary. So here you can observe a simple no load voltage, that is the AC, is the no load voltage characteristics. So you can simply take the graph. So in this graph, AC is the simply no load voltage. That means initial voltage, that is a constant voltage. So when the adjust of series field winding, the load current increases. If the load current increases, the voltage, the terminal voltage also increases. If the load current, that means here if by changing of a series field in the compound generator, so by varying of load current, by changing of load current, the terminal voltage also increases. That means the terminal voltage is more than the constant voltage value, saturation value. That's why this curve is nothing but over compound. So over compound generator. This over compound characteristics. So after that, next, so here you can observe AC curve. That is a flat compound. That means when that, so the series winding having the constant, there is no variations. So in the series winding, there is no variations. due to the there is no change of load currents. At this time we are getting the flat compound, so flat compound characteristics. So in this there is no changes. That means the terminal voltage is always constant. Terminal voltage is always constant due to the change of load current. So when the change of load current, we are getting the constant load voltage. This is a flat compound generator. And then suppose if increasing of load current, the terminal voltage is going to be decreases due to the increasing of series field turns. So that means, so in this, by increasing of load current, the terminal voltage is going to be decreases. Terminal voltage is going to be decreases due to the change of series field turns. So in this type of characteristics is under compound characteristics. So this compound generator characteristics may vary by changing the series field turns. By changing the series field turns. Why? Because so by changing the load current, the series field current also changes. Why? It is both are same. The series field is equals to so load current in the long short shunt in the short shunt compound generator IL equals to ISC. In the long compound generator IL equals to so then IL plus ISH equals to ISC. That means by change of load current automatically change the series field winding. Due to the change of series field winding may increases, may constant or may decreases of the turns of the series field winding currents. So their terminal voltage also increases and constant and decreases. If the terminal voltage is increases, it is over compound characteristics. If terminal voltage is constant by changing of any load, it is a flat compound type. When the terminal voltage is decreases by changing of load current, it is under compound type. These curves represent in the internal and external characteristics. So here we plot the characteristics only terminal voltage and load currents. That's why it is a external characteristics. So here AB is the red line indicates the over compound and the pink line indicates the flat compound. Green line indicates the no load voltage, that's the constant, and blue sky blue indicates the AD indicates the under compound characteristics. These are the characteristics of DC compound generators. And then these are the different type of DC characteristics of DC generators. Now we can see the applications of DC generators. So we have that two types, self-excited and separately excited DC generators. So by taking that separate, suppose if a generator is a separately excited generator. So this separately excited generator, where it is helpful, where we are need to use the separately excited generator. So it is used for boosters. It is simply used in the boosters where we are increasing the voltage levels. So separately we can apply the current. So that is an electroplating processes where it is used for electroplatings, and it is also used for lightning points and the constant voltage purpose. We are using the separately excited generator. Okay, coming to the self-excited generators, first one is shunt generator, DC shunt generator. This DC shunt generators, it is always producing the constant voltage. It is always producing the constant voltages. That's why it is used for lightning purpose or charging the battery point of view, charging the batteries, or it is used for normal general lighting purpose or power purpose with regulators. That means controlling points. So to controlling point of view, by controlling the power in the lightning point of view, power purpose, we are using a DC shunt generators. Okay. So next is DC series generators. So these DC series generators where the maximum amount of, that means a high amount of efficiency, high amount of currents required. So this is used for lightning the arc lamps. This series generators used for lightning the arc lamps, and it is used for constant current generators like boosters. Simply it is used for boosters where we need to maximum amount of power supply. There we can use the series type of DC generators. Okay, in the compound generators is used for traction purpose. traction railway loco. So DC series motors is also used for in the railways. Okay, so railway trains used for trains. Okay, so a compound generator. It is used for compensators for line drops. Compensators like compensate. Compensate means to controlling the voltage drops. To control the voltage drops in the traction point of in the railway traction point of. And also energy transmission over a long distance. We can transmit the energy in a long distance. We can use the compound generators. Okay, these are the applications of DC generators. Okay, so thank you. So thank you for watching this.